Hey guys, so I apologize for not being here today, but I'm really not feeling well, so I'm ducking out a little early, but I don't want to leave you without guidance. So I wanted to talk about the two things that you're working on today. So one, you're finishing up the I do, we do, you do packet that we started in class on Friday. And so we addressed both electrolytic and galvanic cells on Friday. And so today we're starting to talk about non-standard cells. So you've already watched a video about this. I'm not going to belabor the point, but I just kind of wanted to go over a few things. So in a standard cell, the concentrations are always going to be 1 molar. So that means the Q, remember that's the algebraic expression, the reaction quotient, that's the same as K. So Q is always going to be 1 because the concentration of the products over the concentration of the reactants is always going to be 1. Because we're talking about spontaneous cells, that means that K is a large number greater than 1. So when we get a Q that's bigger than 1, that means our cell is closer to equilibrium. And when we have Q less than 1, our spontaneous cell is farther from equilibrium. And so the closer to equilibrium a cell is, the weaker the driving force that pushes it forward, the slower that forward reaction goes. So the cell potential becomes smaller. So that means that when Q is less than 1, so if our cell is not at standard conditions and Q is less than 1, it's going to have a larger cell potential. And when Q is greater than 1, it's going to have a smaller cell potential. And so we talked in the video about the Nernst equation. You do not have to apply the Nernst equation qualitatively on the AP Chem exam. You do have a couple of qualitative practice problems today, but you don't have to apply it qualitatively, but you do have to be able to apply it quantitatively. And so, I'm sorry, you have to apply it qualitatively and not quantitatively. But because we have this natural log of Q expression and we're subtracting that, if Q is less than 1, this is going to be negative. The natural log of it is going to be negative. And so we're going to increase the cell potential. If Q is greater than 1, that's going to be a positive number, and we're going to decrease the cell potential. So when you're asked to justify whether cell potential increases or decreases, you can use a qualitative Nernst equation argument, or you can talk about when Q is greater than 1, it's closer to equilibrium and the driving force is weaker, or when it's less than 1, it's farther from equilibrium and the driving force is stronger, creating a higher cell potential. Okay, so let's take a look at your practice problems for today. And we're going to jump into this one. Okay. So we'll start with the non-standard cells, which are right here. Okay, so when we talk about these non-standard cells, I've already done the I do here, but I just wanted to go over it with you. So we have this thermodynamically spontaneous cell, and we are asked to describe the effect on the value of Q and the cell potential when we make a couple of changes. So the first change is that we add 1/10 of a mole of iron 2 nitrate to the beaker containing the iron solution. So that's going to increase the concentration of the iron 2 nitrate. And if we think about the Q for this equation, it's going to be the concentration of the manganese ions, and because that's a solid, we leave it out, divided by the concentration of the iron ions. So if our manganese stays the same and our iron increases, that makes our Q smaller. And that means that we are getting farther away from equilibrium. And so it is going to increase the cell potential or the voltage. If we add 100 milliliters of distilled water to our iron solution beaker, that's going to dilute the iron solution. That means our Q is going to have a smaller denominator, and so our Q is going to get larger, which is going to make us closer to equilibrium, which is going to decrease the cell potential. And then the last one asks us what happens if we add 100 milliliters of distilled water to both beakers. And when that happens, we're going to dilute both, and Q is going to stay 1, and so there's going to be no change in the cell potential. Okay, so here we have a concentration cell. And what that means is that we have the same reaction happening in both beakers. In one, it's going forward, and in the other, it's going backward. So we have zinc being reduced in one beaker and oxidized in the other. And it's asking us to calculate the cell potential when the right beaker is filled with zinc at a concentration of 2 molar. And so we know if the 2 molar zinc is in this beaker, that the electrons are going to flow from the 1 molar solution to the 2 molar solution, because that will have the effect of decreasing the concentration of the 2 molar solution and increasing the concentration of the 1 molar solution until they're the same again. So it asks us to calculate the cell potential. So in order to do that, we're going to use the Nernst equation. And so the Nernst equation is that the cell potential is equal to the standard cell potential. And because these two are the same half cell, the cell potential is 0 because there's no difference in their reduction potential, minus RT over NF times the natural log of Q. And so that's going to give us 8.314 times 298 Kelvin divided by 2 moles of electrons times 96,485 times the natural log of 1/2. And that's going to give us a cell potential of 0.0089 volts. And so that's coming from the equation E equals E standard minus RT over NF times the natural log of Q. And so that equation gives us a very small cell potential, but there is a cell potential there. And so the cathode is still where reduction takes place. So this is going to be our cathode in the right and our anode on the left, and electrons are going to be flowing from the left to the right. Okay. And then the last thing that we're working on today is Faraday's law. So this is the last equation on the equations and constants sheet that we haven't covered. I equals Q over T. So current is equal to charge over time. Current is basically a measurement of the speed of electricity flow. So the first thing we're going to do is rearrange this equation so that we get charge by itself. So Q is equal to current times time. And we're going to convert our time to seconds because amperes are charge per second. So we need to change that. So we get 300 seconds. Now we're going to plug that current, that 2.5 amperes, into this equation. And that's going to give us 750 coulombs because an ampere is just a coulomb per second. So when we multiply coulombs per second by seconds, we get coulombs. The way we want to think about Faraday's law problems is that they are just stoichiometry where we're adding in the transfer of electrons. So they're stoichiometry where we're concerned with the electron flow. So if we think of that this way, our tin is used as a cathode in this chemical reaction. So we have 1.34 grams of tin plated onto the electrode over 75 seconds. What current must have been used? So I know that current is equal to charge over time. And so I need to find the charge. So I'm going to take my 1.34 grams of tin and I am going to convert that into moles of electrons and from moles of electrons to coulombs. So first thing is to convert from grams of tin, to moles of tin. And from moles of tin, because I can see that I'm transferring 2 moles of electrons, I know that 1 mole of tin is 2 moles of electrons. And I also know that 1 mole of electrons has a charge of 96,485 485 coulombs. That's coulombs. And that is going to equal 2,178 coulombs. So we figured out our charge in coulombs, and we want current. And we know that current is charge over time. So we're just going to plug our charge in here if we can. And we will get a 29.0 amperes. So it's really just one more application of stoichiometry. So as always, if you have questions, let me know, and I will see you soon.